My name is Lauren. I'm the Additive Manufacturing Specialist here at EAC. And for those of you who may not be familiar with EAC, our mission here is to transform the way that companies design, manufacture, connect to, and service their products. So you may be asking, what does that really mean? Well, essentially, we're helping organizations build better products faster, as well as help improve operational efficiencies. And we're doing this by offering engineering and design services like software and support for PTC Creo and Windchill, implementation and training services. We're also offering product and part design services, assessments, and IoT solutions to help companies define a strategy of getting products connected. And finally, the one that relates to the most to our webinar today is that we are a commercial partner of Formlabs. We partnered with them 2 years ago, and this affordable solution gives companies the abilities to streamline their process for designing and make it easier to bring 3D printing in-house. And with that being said, let's turn it over to our Formlabs expert, Kevin, to talk us through the benefits of printing with the Form 2.
Thanks, Lauren, and thanks everyone for joining us. My name is Kevin Gauthier. I'm with Formlabs, and happy to talk to you guys about the Form 2 3D printer today. First, we'll just go over the agenda quickly. So we're going to talk about the Form 2 itself and what SLA 3D printing is, how to achieve great results with SLA 3D printers, some success stories, and then the value we can add to our customers. To get started, an overview of Formlabs. Formlabs is about 400 people. Our headquarters is in Cambridge, Massachusetts. We also have a satellite office in Berlin. 2 factories. We manufacture all the Form 2 3D printers in Hungary. We also manufacture and distribute our resin out of Ohio. We have about 130 engineers and scientists on staff. To position ourselves, there's about 40,000 professional 3D printers installed globally versus about 10 million users of 3D CAD software. When we started out, we wanted to position ourselves between desktop 3D printers that are low cost, require a lot of maintenance and produce pretty low quality results, and commercial 3D printers that make really great parts, but suffer from extremely high cost of ownership and operation, and then lots of service. At the time, we launched the Form 1 and then updated to the Form 1 Plus, and now we're on the Form 2, our 3rd generation printer. And the goal was a low cost, high quality, reliable, and capable desktop 3D printer. To get started, we're going to talk about stereolithography, SLA for short, and how the technology actually works. Like any additive manufacturing process, we build up layers on top of each other. These layers are printed in 2D and then stacked on top of each other to create a 3D model. The materials are special on a stereolithography 3D printer. They're sensitive to UV light, and when they're hit with, in our case, 405 nanometers of UV light, they actually solidify. So they start in a liquid form. When they're hit with light, they solidify. A basic block diagram of the printer you can see here. The top portion is the build platform. This is where your part's actually going to be hanging from and attached to during the printing process. A resin tank. This is what houses our liquid resin that's sensitive to UV light. And then the optical system itself here at the bottom, which draws with a laser to create a 2D slice of your part. 3 major components here in the optical system. We've got a laser diode, which is actually providing the light, and then 2 galvanometers and mirrors mounted to those galvanometers, and those are what precisely control the direction of the laser light. One galvanometer feeds in X, the other one feeds in Y. They work together to draw out any 2D cross-section you need to create one of those slices of your model. We'll dive deep on how the printing actually works. So one common question I get a lot is where the printing actually happens. And it actually happens between the bottom surface of the resin tank and the bottom surface of the build platform. There'll be a gap between here, which you can see. And this gap here in yellow can be either 25, 50, or 100 microns. And that's going to define how thick your layers are throughout the printing process. Once the build platform comes down to the bottom of the resin tank and gives us this gap of this liquid resin, we fire the laser, and the laser actually starts solidifying resin. So you can see the liquid resin in light yellow and the solidified resin here in darker orange. Once it finishes drawing out a 2D cross-section of the part, it's actually going to peel the layer. You can see how the part is actually released from the bottom of the resin tank here. And just a quick video here showing this process. Our peel mechanism is actually unique to the Form 2. We really set out to make a really reliable and capable desktop 3D printer. The majority of our competition is actually directly pulling the part vertically off this bottom surface of the resin tank, but we wanted to do something that would allow more complex geometry to be produced and also less force to be applied to the part during the peel process. So this sliding peel mechanism is going to make the printer more reliable and make it capable of printing even thinner, more delicate geometries, because the sliding peel mechanism reduces the amount of force it takes to peel the part from the bottom of the printer versus a straight pull mechanism. We've also included a wiper on the form too. This is pretty unique in the desktop 3D printing space. The wiper has two major advantages. It's going to agitate the resin. This keeps the heat of the resin actually stirred around and the heat actually equal across all the liquid resin. It also keeps the different components of the resin stirred up and mixed evenly. So agitating the resin is really good for it. The next is for dislodging any cured pieces of resin from the bottom of the resin tank. Any sort of debris that actually cures to the bottom of the resin tank can cause either a mechanical obstruction that would keep the part from coming down as far as it needs to the bottom of the surface of the resin tank, or create an optical obstruction which actually keep laser light from going through that optical obstruction, causing a void in your part which would turn into a print failure. So the wiper is going to maintain the condition of the bottom of the resin tank throughout the print, making a repeatable area to print in that leads to a more reliable printer. Once it finishes drawing and peeling one of these layers, the process repeats, and that is shown here in this diagram where we see the full print process as a whole, starting with our initial squish for our first layer, exposing the liquid resin to a UV light, peeling that layer, wiping, squishing for the next layer, and then repeating over and over again until you get many layers stacked on top of each other to create a 3D model. One last thing I wanted to talk about when it comes to the operation and the features of the Form 2 3D printer is this heater board you can see here on the right. This is pretty unique to Desktop SLA as well. We actually maintain temperature of the resin in the printer, which gives us constant viscosity across all the printers in the field and gives us a more repeatable environment to print in. This is a closed loop system, so the heat is actually provided by this PCB here, and the feedback loop comes from a thermopile, which is an IR camera that's looking at the temperature of the resin in the resin tank and telling the heater board when it needs to turn on and off. Like any manufacturing process, the materials are extremely important, and I wanted to go through each of these materials with you. So to get started, what are the materials actually made of? They're made of monomers and oligomers, which define the mechanical properties of the resin. This is actually the meat of the resin. Photoinitiators, which determine if the resin is going to solidify in one location or not, based on if that section of the resin was hit with the UV light or not. So this is actually what allows the material to cure. And then blocker, you can think of this a lot like sunscreen. This is going to block UV light from the sun or any other ambient UV light in your environment from continuing to cure the part over time. So the laser light and the intensity of the laser actually has to overcome the blocker in the resin. Now for the materials themselves. We'll get started with a standard resin. This comes in black, gray, white, and clear, and it's an acrylic-based resin, has very similar mechanical properties to any acrylic sheet or acrylic materials you've been working with in the past. And it's ideal for general production or general use prototypes and product development sort of work. I personally use it for some mold making for composite parts as well. If you're not happy with the monochrome palette of clear, white, gray, and black, we also make a color kit where you can actually mix your own color of resin. It comes with a base cartridge of a base color material and 5 different pigments that you can mix in ratios to create whatever color you'd like. Then we have a suite of engineering resins. If the hard acrylic resin doesn't have the mechanical properties you're looking for, this suite of engineering resins hopefully will. So engineering resins come in tough, flexible, high temp, durable, rigid, and gray pro, and we'll go through each of those. Tough resin is really designed to simulate ABS plastic. It has a much higher impact strength than our standard resins, and it's really good for things that are going to maybe snap together or have cyclic loading on them that are going to cause fatigue over time. Durable resin is designed to simulate polypropylene material, so it's got some flex to it. It's also really slick and it slides against itself without actually scratching or abrasing itself. So it's really good for any sort of sliding joints. Flexible resin, this is a rubber-like material. It simulates a 80A durometer rubber. High temperature resin, this is for any use case where you might need to expose the material to extremely high temperatures. It's got a heat deflection temperature of 289 degrees Celsius at 60 psi. This is about the highest available heat deflection temperature in the plastics 3D printing market. Rigid, this is one of our newest resins and one I'm the most excited about. It's a glass-filled material, which is ideal for really thin wall parts if you're making like automotive parts such as electrical connectors or enclosures or sensor housings, things like that that have really, really thin walls. This is a great material for that because it's glass reinforced. And then rigid, it has a similar base material as our gray pro resin. It has a similar base material as our rigid resin, but it is not glass filled. So this is good for anything that needs moderate elongation or resistance to deformation over time, but doesn't need the glass fill. And then the last resin we'll talk about here in the presentation today is our castable material, which is designed specifically for investment casting. It's used heavily in the jewelry industry, but we've also seen engineering prototypes built with it as well. And now we'll jump into some details about designing for stereolithography and what the printer is actually capable of when it comes to printable geometry. We'll go through a few slides here with recommendations for things like the top here, minimum supported wall thicknesses. You can see about 0.4 millimeters if you've got some support on the sides of the model, versus about 0.6 millimeters if there's no support at all, meaning this wall actually has to support itself versus having some thicker geometry on each side of it to help it kind of hold its shape. You can actually print unsupported spans with stereolithography 3D printers, which is really unique if you're used to a fused deposition printer. With a fused deposition printer, they're actually extruding plastic. So if you have an overhang with no support under it, it has nothing to deposit that material on. With a stereolithography 3D printer, especially Form 2 with a sliding peel mechanism, the printer is actually capable of printing an overhang with no supports under it, and in this case, about 1 millimeter worth. One of the most surprising things is the unsupported angle. This will actually, the Form 2 SLA 3D printer will actually let you print about 19 degrees with no supports under it at all, which is really, really convenient. It opens up a whole new world of geometry that you can't really produce with something like a fused deposition printer. This is horizontal spans. You can do about 21 millimeters based on 5 millimeter width, 3 millimeter height. With support on each side. And fine details like embossing or engraving, you can see detail of about 0.1 millimeter in an embossed scenario, and about 0.4 millimeters in a engraved detail. And then you need about 0.5 millimeter clearance between two parts so they don't get fused together during the printing process. Holes, we can make a hole of about 0.5 millimeter. And this can be in pretty much any orientation. This makes the printer really capable for things like microfluidic devices or highly detailed valve bodies and things like that. And if you need a drain hole for air evacuation, which we'll talk about in a couple future slides, but sometimes a drain hole is required for venting air during a print. You need about 3.5 millimeters of diameter for that hole. And well, like I said, we'll go into more detail on that when a drain hole is required later in the presentation. The next thing to consider when you're trying to get a high quality part out of a stereolithography 3D printer is the actual resolution of your stereolithography .stl file you're printing. And .stl files are made out of lots of triangles that are stitched together to create a 3D model. You can see on this slide here, this is two models that are the exact same but at two different poly counts. So you can see on the left a model with 50,000 triangles versus the right a model with 5,000 triangles. And because of the detail of a stereolithography 3D printer, if your model is not of high enough resolution, you'll actually start to see these facets in your print. And the model on the right is a great example of that. If we were to print that, we would actually see each one of these triangular faces in our model. And now we get to where I was referring to before about the drain hole. So you need drain holes when you have a cup. And what a cup essentially means is you have hollow geometry with no means of venting air pressure. And what happens over time throughout the print, layer by layer, the build platform going up and down, you end up building up a little bit of air pressure in this. It is very, very small amount of air pressure, but just any difference in air pressure between the atmosphere and the inside of the part will actually cause this issue where this positive air pressure in this void is actually pushing the liquid resin out from under your part, and it leads to maybe voids or pits in your part, but certainly a rougher surface finish than you would expect from a stereolithography 3D printer. Luckily, it's easy to avoid by simply adding a small drain hole to the bottom of your part, about 3.5 millimeters in diameter, to vent that air pressure and allow the resin to settle in between the bottom of the resin tank and the bottom of your part, and not cause the air pressure to push that resin out of there. So here's a quick example. The print on the right would look much better than the print on the left when it comes to the surface quality of the model because this air hole is added. Next thing to consider is the build volume is 145 by 145 by 175 millimeters. If you're printing a really large part on support structures, you need to allow a little bit of clearance around the model to be able to get support structures and their associated bases in the model. So this is a great example. I actually printed about 12 parts that are very similar to these. It's a series of parts that get attached together to make a much larger part. And what I did on the sides here is added a few extra millimeters on each side to give me some clearance for this support structure base to form under the model and give me enough space to print in. When you're thinking about milled geometry versus printed geometry, it's important to think about single bodies versus multiple bodies if you need to make internal right angles. The difference in the two, obviously, is that this model has 3 different bodies that are bolted together. The model on the right is designed for 3D printing, where it's one single body, but we've added a relief around the edges so that your right angle on your piece of machined aluminum or whatever is getting put into this this corner bracket here has some clearance around that corner. Because the print is 3D printed, there will be a slight radius in this area, which could cause your part not to sit square up against these walls. So it is advised that you add a little bit of a relief around your corners. Next, I want to jump into our Preform software so I can show you how to get a model ready for printing. So I'm just going to exit out of the presentation. We'll jump into Preform for a minute, and we'll jump back into the presentation. So this is our Preform software, and we're taking a look here at 2 models that I made recently. And what I'm going to do, you can see their kind of finished version here, but I'm going to actually unsupport them, and then I'm going to walk you through supporting them so you can see sort of my thought process when supporting a model, and some of the things that are helpful when laying out a model for printing with a stereolithography 3D printer. So first, we'll just explore the model itself and some of its details, and then we will get it supported and ready to print. So when you design for stereolithography, you have 2 parts that are going to meet up to each other. It's always good to have some alignment geometry modeled in, so you can see that there is a lip running all around this part. I actually designed this model in inches versus millimeters, so I am going to switch units on everyone for a second. This is a 50 thou lip at a 50 thou height, so 50 thou thick, 50 thou tall. And that lip ended up working out really well for this part. I'm going to get this one supported and show you how that works, and then I'll show you some pictures of the final part and how they fit together once we jump back into the presentation. So just like machining a part, there is some artifacts left by the printer. In a 3D printer's case, those are layer lines. So it's very similar to seeing like machining marks in a machine part. And I'm always really excited to get my machining marks or my 3D printing lines to be something that makes sense and gives a little bit of an artistic effect to the part. So I typically don't print at extremely obscure angles because I like to see something that looks cohesive on the part. So in a part like this, since it is a 90-degree drive bracket, I'd actually like to see the model lines at about 45 degrees. So they run, essentially like this. So I'm going to put the model first in a 45-degree orientation. And you can see with these radio buttons, you can move the model 1 degree at a time. You can also type in a precise degree amount, which in my case, I'm going to go with 45 degrees. And you could essentially print the model like this once we generate support structures under it. But the critical surface that requires the highest tolerance is sort of this lip around the edge because we need it to fit against the negative lip on the other part. So I'm actually going to roll the part on its back slightly, and that'll expose this lip to the top of the printer. That way we have no support structures trying to generate under the lip, and the lip is our most critical surface. So we'll put it upwards so it's away from the build platform and away from the support structures. So if you remember back to the slide on unsupported spans, we can generally run about a 19-degree unsupported span. So that's a good baseline for a degree in this sort of situation. I'm going to go with 20 degrees actually, and you can see I actually went 20 degrees the wrong direction. So I'm going to do minus 40 degrees. So I go back past 0 and 20 degrees in the direction I actually wanted, which is like this. So we have the part laid back at 20 degrees. It's at a 45-degree angle when it comes to the parallelness to the build platform. So this will put our layer lines at straight through the model like this, and in relation to the 90-degree drive at a 45-degree angle. So it should look really cool once it's printed. Now that the model is in an orientation that we like, I'm going to generate support structures under it. So I'm just moving down to our supports tab. I'm going to click generate selected. And the support structures will now generate under the model. This is just going to take a second here. Okay, our support structures have now been generated, and now we can do some manual editing on these support structures just to clean it up. You can see a couple areas that probably don't require supports are areas like below these bosses where the screws are actually going to be screwed into. And the way you can tell if support's required or not is actually sliding through a preview of your build. So if you look at the right side of the screen here, you can see the slider, and right now we can see the entire model. Once we begin sliding the slider up, we can actually see sort of a play of the model as it's printing, and you can see which layer we're on here. So right now we're on layer 194, for example. So I'm just going to slide all the way up to the top so I can see where I am, and then I'm going to start sliding back down and look at an area around one of these bosses like this to see if I have what's called an island. If I have an island, I'm definitely going to need a support structure under it. So you can see right here there's an island, and that means that we need to leave support structure in that area to support this island. You could essentially change the angle of the part to reduce this and maybe eliminate that island altogether. But in my case, I'm really happy with the orientation itself, and I wanted to leave it alone. So I'm going to leave the island there, and I'm going to leave the support structure as is in this case. And since all the bosses are the exact same design, I know that all the bosses are going to need that support structure under them to support that island. So I'm going to leave all support structures under the bosses alone because we know that they're each going to require that support structure. So we won't change anything there. But one thing we will change is support on this hole, because the printer prints circular geometry like this really well without needing a support structure. So I'm just going to come in and edit, and then I'm going to click on this support point right here and actually remove it because I don't really need a support there for any reason. There's another one or two more over here, so I'm going to get rid of both of those as well. And you can click on each individual support. You can also click and drag a box over them and select multiple at a time. But I'm going to just individually select each one because I'm not removing very many of them. So that one I don't really need as well. This is one of those things that the more you print, the more you get comfortable with this, and you start thinking your print through from the beginning and designing around where the support structures themselves are going to go. And that's the case for this part for sure. So I'm going to hit apply my edits, and now those support points are going to be removed from the tops of these holes where I don't really need them. Another thing is these two internal supports here, there's clearly no island under these, so we don't even really need to check the slider on them, but we can anyway just for good practice. We can see that there's no island in this area, and I'm going to turn the model around so you can see a little bit better. There's no island in that area, so that support structure is pretty unnecessary. So we're actually just going to remove those two as well. This one. And this one. And we're going to apply those edits. And now this model is really cleaned up and ready for printing. So the last step is just make sure your print settings are set as you want to. So we can click the print settings window, and this is just where you're going to select your material, what version number it is, what layer height you'd like to print it on. I don't currently have a printer connected to this computer, but if your printer was on the internet on your Wi-Fi or plugged in via USB or Ethernet, your printer would actually show up here, and it would default to the material that's actually in the printer. So since there's no printer, this is manual selection, tough V5 in 100 micron. I'm going to click apply. The last setting here is just determining where on the build platform you want to print the model. If you print biased towards the wiper side, you'll get a slightly faster print because the wiper doesn't have to go quite as far. So for quickest printing, you would bias towards the wiper. Maybe you need to lay out multiple parts. You can clearly move this around in wherever you want and set it where you want and hit print. So here's the print button, and you would send this over to the printer this way. That's it for preform. I'm going to jump back into the slides. And we'll get to see the finished version of that part once the slides load here. So here's actually a quick GIF of the two parts, top and bottom, actually getting pressed together. So you can see that lip really fits well once you press the parts together. And you might be wondering what this model is actually for. Here's some of the finished gearboxes. These are actually the straight sections. There's two straight sections and one 90-degree section. And those work together to create this rotor casting device that I built for a project I'm working on. Once the parts are printed, they need to be finished. And the main thing about stereolithography 3D printed parts is they come out of the printer with excess liquid resin on them, and that excess liquid resin needs to get washed off. You wash the parts in 90% isopropyl alcohol. This is a standard finish kit that comes with the printer. It has two tubs. One is your kind of dirty tank where you're going to soak the parts. The other is your clean tank where you're going to do a vigorous rinse of the parts. It also comes with a few tools like a jig to hold your build platform, a scraper, some clippers, tweezers, and a part removal tool. But we know that manual finishing of the parts is not ideal if you're doing a lot of volume or you have obscure shaped parts that are more difficult to clean. So we've actually come up with our automated post-processing equipment, a washing machine called FormWash, and a curing machine called FormCure, and I'm going to walk you through those. First is the FormWash. It's the automated washing machine. Uses an impeller to agitate isopropyl alcohol and wash your part. What's really awesome about FormWash is it's got a motorized sort of dunking system that actually dunks your part into the isopropyl alcohol and washes it for a predetermined amount of time. Once it's done washing, it actually removes the part and the part begins to air dry. This is great because it gives you consistent wash time, and you don't have to worry about removing the part from the alcohol in the appropriate amount of time. Instead, the machine handles everything for you. FormCure, this is good for any post-curing you'd like to do to parts. All the parts actually do get a little bit stronger if you do a post-cure on them. With our standard materials, it's not really required, but they do get a little bit stronger if you do post-cure them. Some of our other more exotic materials, like our engineering materials, do require post-cure. So it's a great unit to have if you're going to use something like tough or flexible resin that requires post-curing. What's awesome about this machine is it's got 13 LEDs that emit 405 nanometers of UV light. It's LED versus incandescent, so it's got a really long lifespan. But it's also got a heater that'll actually heat the environment up to about all the way up to 80 degrees Celsius. And that along with the UV LED light goes hand in hand to post-cure parts as quickly and as strongly as possible. Once you've washed the parts and maybe cured them, you need to remove the support structures. So you can see here in this animated GIF some of the support structures being clipped off by clippers. Clippers is one method. Some people kind of twist and pull and rip the parts off the support. Really depends on how delicate your geometry is and what you're trying to accomplish with the part. But generally, removing the supports is part of the process. Next, you can do any secondary steps you'd like sanding on the left. The material sands really well. I actually make molds with the machine, so sanding is a big part of my personal life with the printer. You can start at anything like 200 grit and go all the way to as polished as you want, sometimes even like 1,000 or 2,000 grit if you're trying to make a light pipe or some sort of optical instrument. On the right, you can see coating with mineral oil. This is pretty common if you have pieces that are going to slide against each other, like a clip or a hinge of some sort. Mineral oil works really well to coat the parts and make sure they slide against each other really well. Then we'll jump into actually building prototypes with the printer and some examples from some of the customers. So first we're looking at Paralens. This is a really sweet underwater flashlight that was all prototyped on Formlabs SLA 3D printers, and you can see the model in the image is actually 3D printed parts. It does look like a final version, but that is a prototype. This here is an electrical instrument. You can see how the fit works. We've actually printed 2 different parts on this device. So the case itself in black resin, and then the buttons in our flexible resin. You can test multiple design iterations. So here's a third thumb designed by Danny Claude, and this is you can see multiple iterations of the device all printed on Form 2 in multiple different materials. So we're looking at grays on the top left, tough in the sort of middle of the screen, and then some black resin down here. So multiple different resins, multiple different designs can be tested very quickly with a Form 2. Suture, this is an automated suturing device. So essentially a machine that can sew tissue together. And you can see in the top left image, lots of different design iterations, different geometries to fit in different locations where they're actually using this on a patient. And what's really cool is the use of universal parts in this model. So some of these heads are configured in different orientations, but they use similar standard parts. So you can swap different heads onto the drive motor here, and a lot of the parts fit between the different iterations. So that's really exciting. New and pretty popular use case for 3D printers is jigs and fixtures. So we can see a traditional jig and fixture would require lots of different steps and an external vendor to actually deploy those parts. With a Form 2, you can really simplify that workflow because you can produce those jigs and fixtures in Office. And here's a great example of one. This is a machining fixture that fixtures a part while it's getting some post-processing done on it, some post-machining processes done on it. So you can see the cost savings here, $379 for machined aluminum, $226 for HDPE, and $13 in tough resin printed on our printer. It's really cool because you can get a tighter feedback loop between your tooling and your production and assembly workers. You can quickly iterate and change designs, and you're really empowering your engineers to create their own fixtures and tools in Office, which leads to housing digital inventory. So you can see a company like Pankel Racing that we're using as an example here. They have tons and tons of these fixtures, so they can quickly get an ROI on the printer, which we're going to look at in a second. But beyond that, they can actually hold all these models in digital inventory, and if one were to break or get lost, or they ramp up production and need multiple of these fixtures, they can just easily produce another one with a Form 2 SLA 3D printer. Some unique things that Pankel does with these parts, they actually put identification numbers into them so they don't get them mixed up. And some of the bottom line results, there's a 90% cost savings compared to outsourcing the machines. The lead times reduced significantly, and there's no minimum order quantities, which allows them to create more designs much quicker at a lower cost. I just wanted to click through a few of these jigs and fixtures that aren't the specific ones that we looked at a minute ago. Just some more examples, just to open your mind to what's possible with the SLA printer when it comes to fixtures and jigs. So here's a drill guide. Here's some soft jaw inserts, assembly jig that we actually use for producing the Form 2 printer itself, a disassembly fixture for unsnapping the top and bottom shells of this enclosure. And then we'll look at ROI case. So we'll go back to our jig from Pankel Racing, and you can see we can get a ROI at 14 units on this fixture versus machined aluminum. 22 parts with HDPE. So you can see if you're doing 15 to 20 fixtures a year and about this size, you'll get a return on investment in your printer in under a year. And this was the math that calculated it, about a $5,000 average order size for the printer, the difference in cost between the machined aluminum part and the printed part, and that equals your ROI at 14 units. If you want to take a look at ROI on your own parts or how much where your ROI point might be with your application, you can simply navigate to our website and click on formlabs.com/ROI, and we've got an ROI calculator that'll allow you to take a look at your own designs. Last thing I want to talk about today is the support and how the printer is warranted and supported. So really we have two different types of service offering for the printer. The first is a 1-year warranty that's included with all printers, and this covers your parts, labor, and shipping back to our factory. We can extend that warranty to 2 years for an additional $500. And then the second thing we'll talk about is the Pro Service Plan, which is an additional level of service that's going to add phone support, expedited RMAs, and a web-based training session with one of our customer support engineers. And that starts at $499 for 1 year and $899 for 2 years. I want to thank you for attending today, and please feel free to reach out if you have any questions. Lauren Adey at EAC is their additive manufacturing specialist, and she'd be happy to help you out. Thank you. Have a good day. Bye-bye.